Hello my dear, I welcome you in this session of Basics Thermodynamics. My dear, what is the motive of this session? The motive of this session to enhance your GATE score. In this session, we will cover all the advanced problem with respect to the 2024. One thing is very important in this session, Vita. While you attempt this session, you must feel very comfortable for the period of 3 hours. You feel very comfortable, and also you have a very motivated. Why? Because what is the problem in this session? We already selected that problem. Really is very good problem, and if you practice or if you revise your session, revise your all the concept according to this session, according to this level, you must have a very much confidence about that. Okay, so we'll start the first problem. So we'll take the problem from step by step. So in the thermodynamics, majorly there are 3 portions in which the question will ask. Okay, supposed to be asked. The first portion is the first law of thermodynamics. That means, in generally, the first law of thermodynamics is have 3 contests. First is the closed system contest. That means energy application, closed system, energy application, open system, and energy application of unsteady flow problem. So any of these 3 domains, you supposed to be the question will ask in the GATE 2024. Previous in GATE 2023, the unsteady problem will already asked. So it may be less chance, but you don't ignore that. Why? Because unsteady flow problem is a very good problem. Okay, in this contest. Number first. Number second, then after we have to enter in the second law of thermodynamics, in which we have to design the engine or a working device, output working device, or input working device. So accordingly, we have to take a different type of engines, and we have to analyze that engine of a performance like efficiency. And also from the efficiency, there have a ideal things, that means a reversible engine. We have to suppose to that a reversible engine, and we have to compare with that one for the irreversible heat engine, irreversible process. Third thing is that then if you have to compare the extent of irreversibility, that means if any practical things is there, and if you compare with the ideal one, that means if you compare with the reversible one, there must be a quantitative parameter, that is a dq by t, that is for a reversible system, for a reversible process, that will denote the entropy change. So we have to balance also the entropy. So in this contest, we have to balance 2 things. First, the energy balance. Second one, the entropy balance. From these 2 concepts, the questions must be asked in the basics context of a thermodynamics point of view. So let's start the today's session, and the first question is your this one. Please, this is the question related to your work and heat transfer. My dear, this is a easy problem, but while you are attempting the examination, such type of problem, really this problem is very challenging. Why? Because generally the thermodynamics work, if you view about the thermodynamics work is generally the reversible work, and also called the displacement of a boundary. The boundary displaced, the work will develop. Okay, so the boundary displacement work. So this question related to the displacement work. Okay, one thing is very clear. I am saying that very subtle concept is that PDV work, that means a thermodynamics work, integration PDV work need not be applicable only for closed system. It may be applicable for the open system. The limitation of this PDV work is only quasi-equilibrium process of a simple compressible substance. Okay, simple compressible substance and a quasi-static process. That's it. It is not like that a constant pressure process, constant temperature process. No, and it is a closed system only. It is an open system only. No. Only thing is that there is 2 things for a internal reversible process, and the process that is irreversible process. It must be a quasi-equilibrium process. So there must be a quasi-equilibrium process, and due to that, the displacement of a boundary, either expansion or a contraction, we have to apply this equation. It is not necessary that the system is a closed system. Okay. So read this question. First question. These are the cylinder. These are the cylinder. Okay, and these are the piston. Pistons attached with a pin. Okay, so there are a different content. There is a piston. This is your cylinder, thick cylinder. Why? Because the dimension of the piston, it is also given, and the piston with the cylinder will attached by the pin. That means this pin is holded as a cantilever point of view, as a cantilever. That means this end is fixed like that. Okay, cantilever, and this is end free. So it will be holded by this piston. I have a thick size piston will is holded by this pin, and due to the chance of the piston, it may be move out from the cylinder. So there must be a two stops to withstand, to never allow the piston is moving further. What is that? A thick piston initially held in a cylinder by a pin. Okay, so as shown in figure, assume that the cylinder contains a carbon dioxide, number first. So in this one, we have to assume the carbon dioxide act as an ideal gas. We have to assume like that. Okay, this is the first attempt, and the cylinder contains the carbon dioxide. That means this is our system. This container is our system. This carbon dioxide is our system. This carbon dioxide is our system. 1 second, beta. Okay. This carbon dioxide act as a system, and this pressure, the pressure of the carbon dioxide is 220 kilopascal, and take the ambient temperature. What is the ambient temperature? Ambient temperature is 300 Kelvin. The density of the piston, it is given. Why density of the piston is given? Why? Because we cannot ignore the piston weight. Why? Because it is thick. So for the weight calculation, the density of the piston, it is given. Assume that the atmospheric pressure, what is the atmospheric pressure? That means we moving it, either it move up and down, it is moving against the atmospheric pressure of 100 kilopascal. If the pin is removed, what's happened? It may be fall up, it may be fall down, it may be move up. It will be, it depends upon the given condition. So assume that the assume atmospheric pressure is 100 kilopascal. If the pin is removed, then the piston will move up. It is given. It says that after you removing the pin, piston will move up. That means it must be the pressure inside. That means what is the force which is holded, which is lift the piston at this position? That pressure is higher than the outward pressure, so that if the pin is removed, the piston will move up. Okay, assume that after a while the gas, this line is very important, I'm telling you. Assume that after a while the gas return to ambient temperature under these circumstances. That means what is the final state of this piston? That means after removing the pin, piston will move up, and it may be touch the stop or not, we'll discuss. But after a while, the temperature is again to the atmospheric temperature. That means your ambient temperature. Okay. This says that, please check that whether the piston will touch the stop at the top while moving up. This is the very important question. This says that, hi Rahul, hi. Everyone, good afternoon, beta. Good afternoon. Everyone, good afternoon. Just try to that. We'll check the piston will touch the stop or not. We'll check the piston is touch the stop or not. How to check? How to check, beta? Question will clear? Now, go to the next. Now, my dear, let's draw the piston cylinder arrangement with the pin. Before that, the piston dimension, that means all the dimension of the cylinder given. This cylinder, it is the piston, that means this is your cylinder piston. So, the piston is moving upward. the piston is moving upward. The piston is moving upward. Thank you, Sandeep. The piston is moving upward. Now, when the piston is moving upward, after the removing the pin, we have to check under which pressure, what pressure is responsible to move the piston. How to calculate that responsible pressure? We have to calculate the responsible pressure by, we assume the piston is in a static equilibrium condition. So we have to find the piston pressure, that means what the pressure the piston will move. We have to balance the force balance of the piston. So we have to take a piston. This is your piston beta. This is your piston. Okay. Okay. This is your piston. And on this piston, this is your free body diagram of the piston. Okay. So this is your free body diagram of the piston. No problem at all. Now, what is the given condition? First, assume. What is the assumption? Carbon dioxide act as an ideal gas. Ideal gas. Carbon dioxide act as an ideal gas. First assume. And state first it is given. Initial state first it is given in the question. What is the initial state given, beta? The pressure P1 it is given 220 kilopascal. Okay. State 2 it is given. What is the state 2? What is the state 2, beta? Please. The state 2 is what? The state 2 says that assume that after a while the gas return to the ambient temperature under these circumstances. That means what is the final position? T2 is the same as the ambient temperature. Okay? That means T2 is your T2 temperature at point 2 is equal to temperature ambient, and that ambient temperature it is given 300 Kelvin. Yes or not? Ambient temperature given 300 Kelvin. Okay. Volume calculation. How to calculate the volume? Volume calculator calculate karna hoga. Please calculate it. Now, this is your free body diagram. Free body diagram of piston. Please see very carefully. I am telling you, you can never find such type of question on any YouTube channel. It is my challenge. Okay. So, what is the free body diagram? Free body diagram, it is nothing. We have to draw at equilibrium. We have to draw the free body diagram at equilibrium. At equilibrium. That means what we have to draw the free body diagram, that free body diagram is at equilibrium. So the net force on the piston is 0. So what is the force in upward? The same force is downward. We have to take like that. That means, and when we have to draw the free body diagram, we have to find what the pressure, the piston will move. That means after removing the pin. That means after removing the pin, piston will move up. So what is the pressure responsible to move up the piston after removing the pin? This is a very simple funda. So if you remove the pin, piston will move. So what pressure is responsible to move the piston? That pressure is known as equilibrium pressure. That pressure is known as equilibrium pressure. So from the lower side, this is your pressure which is exerted by the carbon dioxide, which is responsible to move up. So this is your P equilibrium into area. Area is what, beta? Cross section area. This is the force which want to move up. Now there is a weight of the piston downward. Weight of the piston downward. Mass of the piston into G. This is the weight of the piston downward. Now there is upward is atmospheric condition. Upward is atmospheric condition. So it will act as a distributed. So same pressure. So this is your P naught into A. This is your cross section. Now is there any force other than this one? Is there any force? Please everyone. Please everyone. Is there any force? No. There is no any force. What is this force, beta? This force is the pressure exerted. This is what, beta? Force exerted by the gas on the piston. Very important. This, see my dear, thermodynamics, the language is very important. So this is the force exerted by the gas on the piston. What is this one? What is this one? What is this one? This is the force exerted by the atmosphere on the piston. Clear? On the piston. Now we have to balance it. So P equilibrium downward into area down, upward. Downward is atmospheric pressure plus weight of the piston, mass of the piston into G. So from here we have to find equilibrium pressure. What is the equilibrium pressure? P naught plus mass of the piston into Z divided by area. How much it is, beta? Please everyone tell me. Please everyone tell me. Yes. Yes, yes, yes. P, wait, wait. Now how to calculate after this one? Many students now putting the value, mass, density or mass by volume. What is the volume? They are calculating each other. Don't calculate this one. Simple funda at this point. What is that? See, this is your pressure P naught plus. What is the mass? What is the mass of the piston? We know that density of the piston, it is given, is equal to mass of the piston into volume of the piston. Yes or not? And what is the volume of the piston? What is the volume of the, yes, pressure is 2 point, wrong. Wrong, Rahul, the pressure is wrong, okay? So what is the, so density, what is the mass? Mass, so this is your density or mass into volume. So density is equal to mass by volume. So what is the mass of the piston? Density into volume. Now what is the volume of the piston? See, what is the volume of the piston? This area cross section into height. Height is what? 100. So cross section area into 100. Cross section area of the piston into 100. 100. This height is your not total height. This piston height 100 into cross section area is the volume of the piston. Okay. So this density into what is the volume? Cross section area A into height of the piston P. Okay, put this value here. So this is your density area into height of the piston into G divided by area. Area cancel. What is this? Then what is this, beta? That means P naught plus rho GHP. See my dear, this is the equation of hydrostatic. This is the equation of hydrostatic. See my dear, this is the equation P equal to P naught plus rho GH. That means, yes, if the pin is removed, piston is floating condition. Piston is floating. So for the floating, what is the pressure at this point? Atmospheric pressure outside plus the pressure which is responsible to the weight. So P naught plus rho GH of the piston. Okay. So put all this value. What is the value of all this one? We have the value of all this one. What is the value? Please, all this value put here. So I'm writing here. Density of the piston, it is given, beta. Density 8000 SI unit. Height of the piston 100 mm. So this is 0.1 meter. And G is equal to 9.81 meter per second square. Put this value here. Put this value here. If you put this value here, this is equal to 107.85 kilopascal. This is the pressure at which, after removing the pin, piston will move up. Rahul, it is clear, beta. Rahul, it is clear. It is clear, everyone. Please tell me. Now, so this pressure is responsible to move up. Now, my dear, whether this pressure is able to move, due to this equilibrium pressure, piston will move up. Now, my dear, whether this pressure, yes, 107, correct. So, please tell me, beta, whether this pressure is that much sufficient so that the piston will hit the stops. We'll check like that. See, what is there? This is there that under these circumstances, whether the piston will touch the stop at the top while moving up, we'll check like that. So for this type of question, first find the equilibrium pressure. And then how to check this pressure is responsible, this pressure is that much responsible. No, Rahul says that no. How, beta? How? Yes, it is. How to say that, Rahul? How to say that? Please think like that. This is very important thing I am telling you, never found in any YouTube channel like that. See, P1, P2, T1, T2, all the problem it is available. But what is the analysis? That analysis is very important. Now, my dear, see, if you find, I am telling you a subtle concept. If you want to understand that, sir, the piston will touch the stop or not, first find the equilibrium pressure, then the second step, very important. The second step is that, sir, we have to assume the piston will touch the stop and find the pressure according to the touching the stop, compare with them. Then you have to conclude it. Otherwise, there is no any other method. So, for that one, we have to assume, hypothetically, that means very important, very important. Okay, what is that? Now, hypothetically, assume that the piston hit the stops. You have to assume like that. Other than there is no any criteria. At this stage, That means piston will touch the stops. According to the question, what is the final temperature? The final temperature is the ambient temperature. That means T2 is equal to what the T2 temperature? T of the stops. Yes or not? And that T2 is equal to ambient temperature. Now, my dear, there is very important information in this question. What is this says that? This line, return. There is a return is given. That means return to the ambient temperature. That means initially it is ambient temperature. And return to the ambient temperature. It is not given that assume after a while the gas return. That means what is the final is the same as the return to the atmospheric return. That means initially it is also atmospheric. Okay. So this is equal to T1. This is your main important thing. Why this is? You can write like that because gas return to ambient temperature. Now, so my dear, initial temperature and final temperature are same. That means we have to apply the ideal gas equation. We know that P small v you have to take like that R into T. That means final is P2 into V of stop final divided by T of stop is equal to P1 initially, V1 initially, T1 initially. This T1 and this T1 is cancelled. Now what is P? So what is P final? This P2 is what, beta? We have to assume this is a stop. So what is this one? P1 V1 by V of a stop. Now if you find this one, what is P1? P1 is 220. P1 is 220. P1 is 220. And what is V1 initial volume? Initial is what? Area is same, na? Cross-section area both are the same. So only, why? Because volume is what? Volume is what? Area into cross-section area into height. So cross-section area for this one, cross-section area for this one are same. So only height matter. So what is the volume, initial volume height? When the piston is initially volume V1, what is the height? 100. What is the final height? Please comment. What is the final height of the piston? What is the initially movement of this one? What is the final movement height? Please comment. Everyone, please comment. What is the final movement height? Initially movement height is this one, 100. What is the final movement height? When the piston will touch the stop, what is the height? Please tell me. What is the height? Please tell me. What is the final height when the piston will touch the stop? No, that is wrong. Papa ji, that is wrong. That's why I am asking. This knot will travel only one. Yes, 150. Yes, Papa ji, I think you have to write 200. It is right. Papa, you are right. That means this 100 is reserve. It is not moving. So 100, this 100 plus 150, 150 is the total height, which is the final height. Okay? You are not. Rahul, no. Not 250. Rahul, you are wrong. Papa, you are right. 150 is there. Why? Because 100 is always reserve. Where the piston is there, 100 is always reserve. So how much it will travel? If you measure from this reference line, 100, and if you measure from this one, so 100, this one, traveling is 50. Why? Because 100 is reserve. So total traveling is 150. Right. So 150 is there. So this is your 0.1. Yeah, 100 divided by 150. How much it is? How much it is, beta? This is your answer is 146.66 kilopascal. Now, my dear, this is the pressure where the piston will touch the stop. The pressure, this is the pressure when the piston will move. Yes. Yes, it is right. Now analysis is very important. 146, right, Rahul? 146.66. Now, analysis is very important. I'm telling you, very, very important. Now, what is this pressure? What is this P2? P2 is the pressure when the piston will touch the stop. Okay. What is this pressure? What is this pressure? This pressure is the pressure when the piston will move up. Now, so the pressure is increasing or decreasing? See, the pressure is increasing. This is 170 when the piston will move up. And when the piston is touching the stop, there is a 146, 147. So the pressure will increase. When the pressure will increase, when the system pressure will increase, let's suppose at 107, the piston is moving 107. This is equilibrium pressure. That means 107 moving. Yes, increase. That means 107 pressure, piston will move up. Now it will touch the stop. Now now it will increase the pressure. That means it already hit the stop. So that the pressure will build. In any system, how the pressure will be built? When there is no any, then that means you have fixed the volume. When the fixed the volume, when the piston will touch the stop. That means the equilibrium pressure is less than the final pressure. The equilibrium pressure is less than the final pressure. Piston will hit the stop. That's it. Piston will hit the stops. If the final pressure is less than the equilibrium pressure, piston will doesn't hit the stop. If the final pressure is exactly the equilibrium pressure, piston will just touch the stops. So there are three conditions. Piston will hit the stop, piston will touch the stop, and piston will not touch the stop. So first find the equilibrium pressure, and if the inside pressure is higher than the equilibrium pressure, that means already piston will touch the stop and stop never allowed to go further, so automatically the pressure will build up. Automatically the pressure will build up, so the piston will hit the stop. Clear? Please tell me. That means, hence, P of a stop or final pressure or P2 pressure is greater than equilibrium pressure. Is greater than equilibrium pressure. Yes, question is highly conceptual. That means final pressure is higher than the equilibrium pressure. That means piston will hit the stops. That means, hence, piston will touch the stops. Piston will touch the stops. Okay. Now what is the condition if P equilibrium is greater than this one? What is the condition if, note, if P equilibrium is less than P of stops. What is your conclusion? Everyone please, Rahul, please tell me, if P equilibrium is less than P stops, then? If P equilibrium is less than P stops, then piston will doesn't hit the stops. Piston will, that means piston will doesn't hit the stops. clear beta? Clear? Rahul, Papa, everyone please. It is clear beta? This is clear now? So that is the very important, while we are solving the thermodynamics question, such type of analysis we have to miss it. Yes, not hit. Yes, not hit. Okay. So how to hit the stops, not hit, that is the logic. Okay. So really this is very good questions. So please like and up appreciation भी कीजिए. Now my dear, see, if you impressed, then let's suppose, see, I give one information. If you find such type of context, see, it is that if you find such type of things, see, the IMS provide, there are different features. What is the features is that, beta, we have to provide 800 plus hour live classes with the interaction. 800 plus live, plus theory book, exercise book, 30 plus year gate question bank with video solution. What is that, beta? What is the... we'll discuss. Rahul will discuss. So, theory book, exercise book, 30 plus year gate question bank and with video solution. You can never found in any question bank have a video solution, but our question bank have a video solution. Very important. And also, there is not a single method. If you, the PYQ have not a single method. Minimum 3 method. Approximately, you can see that minimum 3 method, particular for my subject, thermodynamics subject, there are 3 methods. One question, 3 method is there. 12 personalized one-to-one mentorships. That means we have to giving the one-to-one mentorships in 12 personal mentorship. That means you can ask anything for a particular teacher if you join this course. And 130 plus online test with the video solution of a mock test and many more. So if you have any query regarding this one, so you can, here you have a description in that box, and also you can call this number 96633726248 or 777188155588. Okay. Now the second information is very important, that we have also Telegram group. On that group we have to all the update, time to time update is there, and also there is a schedule for free. That means what is the free lecture is there on YouTube. All the schedules mentioned, that means all the time, that means what is the routine, what is the structure of the YouTube. All these are mentioned on this Telegram group, so you can join this with this one. And also important update related to the seminar, webinar, or all the exam information. Or also there is all the exam information notification is there. There is a free of cost, you cannot pay anything. And expert session on important topic, okay, expert sessions, okay, and daily quiz and many more. The quiz is very important on the Telegram, I'm telling you, okay, beta. So these are the features. Now come on with Rahul asking that कि sir, Rahul asking that कि sir greater होगा क्या मतलब? What is that? Oh, greater than क्या होगा? अरे P equilibrium, right. Oh, no, this is a greater than, this is same thing. Greater than. See, this is less than. 1 second, beta. One second. It is little bit confusing. Don't read. If P equilibrium is greater than, this is your equilibrium pressure, it is typing mistake. This is equilibrium. If P equilibrium is greater than P of stop, that means stop pressure, that means at the stop. So please understand this concept. I will tell you. See, equilibrium pressure is what pressure? And that pressure the piston will move up. Now, if you find the stop pressure and the stop pressure is less. So if the stop pressure is less, that means that equilibrium pressure, see, due to this equilibrium pressure, the piston will move up. Like finally, the pressure will drop. So that this equilibrium pressure is not much more enough, so that piston, so it is not hit the stop. See, if this is your piston cylinder and this is your piston, so from this equilibrium pressure, piston will move up. Now, while moving up, this pressure, that means at the stops, this equilibrium pressure is increasing. That means higher the equilibrium pressure as compared to the stop pressure. That means at the stop pressure, the pressure is low. At the stop pressure, the pressure is low. So already piston doesn't hit the stops. That means you can assume that the piston is hit the stop. So if hit the stop pressure is higher than the equilibrium pressure. The stop pressure is higher than equilibrium. So in that case, the piston will hit the stop. If the equilibrium pressure is greater than the stop pressure, piston doesn't hit the stop. And if equilibrium pressure is equal to the stop pressure, piston will just touch the stop. Rahul, it is clear, beta? Rahul, it is clear? Please reply in the chat box. Okay, now. Now, see the next problem. This is your next problem. So that question is from the basics, and this is the question is related to the steady flow. Same question. This same question asked in GATE already, but this is the different question. It may be supposed to be asked in the upcoming GATE question. Please read the question carefully, beta. I will move. Please read the question carefully. What is that? There is an electrical heating system. There is an electrical heating system. Okay. So this is any duct is there. So in duct there is a flow of air. This is a simple problem. Okay. In the duct there is a flow of air, and you are heating with the electrical heater. And this arrangement is used practically in that situation where the house, heating the house room consists of a simple duct with a resistance heater. So there is a resistance heater. Air is heated. That means in this, what is the air it is flowing? That air is heated by this resistance heater. Consider a 15 kilowatt electrical heating system. So this is the work input. Why? Because electrical heater is within the system, so it is not a heating effect, it is a work effect. If the electrical heater is outside the system, that is your heating effect. If the electrical heater inside the system, that is your work effect. So this is the work, electrical work into the system. Okay, heating the system. Air enter the heater section at 100 kilopascal. That means what is the air which is entering? That is the, what is that? 100 kilopascal. That means at this pressure the air is entering, and at 17 degrees centigrade with the volume flow rate. That means what is the rate? That means this is the discharge. What is the discharge? It is given 150 meter cube per minute. Mind it is not per second. If heat is lost from the air, that means this is non-insulated, that means it is not insulating, so heat may be out. So heat out, it is your 200 watt. Determine the exit temperature. That means what is the exit temperature at T2? What is the exit temperature at T2? So you have to find the exit temperature. Clear? Clear? So we'll start this problem. So find the exit temperature. Okay, so simply, this is a very common question in the thermodynamics. You may have to, this type of question you are also in the RAC, this type of question also in the entropy balance, this type of question also in the exergy balance, everywhere. Okay. So what is that? There is a section, heating section. That means this is your heating section. This is your duct is there. This is your duct, and this is your inlet section. Okay, this is your exit section. So this is the duct, inlet section and exit section. So this is your I, and this is your E, exit section. Clear? This is our control volume. This is our control volume. Why? Because this is an open system, so this is our control volume. Okay, these are the control volume. What is the property it is given? There in this one there is air is in, air in, that means cold air, let's suppose cold air in, and at this portion cold air out, hot air out. Okay, this one hot air out. So at this section hot air out या hot air exit. Okay, the air, cold air in of a volume, what is the condition it is given at inlet? Inlet pressure it is given, how much it is? 100 kilopascal in the question. Inlet temperature it is given 17 degrees centigrade, and the volume flow rate it is given 150 meter cube per minute. This is the volume flow rate. Okay. What is the purpose? To heat. So there is a electrical heating device it is given. This is electrical heating system on which we have to apply the electrical work. So we have to do the electrical work, W electrical in. This is the W electrical in. Electrical work we have to do, not heating effect. This is the working effect. This is your working effect. Why? Because the work is in. Why? Because this heater, it is within the system. If this heater is outside from the system, that is your heating system. If the heater, it is inside the system, that is your work effect. Okay? Clear? So they are asking that what is the exit temperature? What is the exit temperature? And also it is given the heat loss from the system. Heat loss, that means heat out. How much it is? 200 watt heat out. Okay. So this is your, how much it is? 21. Very good. Very good. 21. Very good. So this is your steady flow device. So for the steady flow device, the mass of the control volume with respect to time, it is 0. And the energy within the control volume with respect to time, it is 0. We know that these things. Okay. We also take that change in kinetic energy and change in potential energy is equal to 0. Why? Because we have to balance that. So what is the steady flow energy equation? Steady flow energy equation. What is that, beta? We know that. This one. Heat transfer plus MI, M dot I, inlet HI plus CI square by 2. Inlet it is, beta, GZI is equal to W dot plus M exit dot H exit CE exit K square plus ZZ exit. We know this thing. This thing we know that. If you don't know, you not qualify 2024 examination. If you don't know, you not qualify 2024 examination. This is damn sure. Okay? So you must be know that. Okay? Now, so there is no any kinetic energy change, potential energy change. It is given, we have to assume that. And also there is a heat transfer, that means there is a work, it is a heat transfer, that means this is heat is what? Q out plus, so we have to write minus, this is our out now. In this equation is written by the positive sense, that means heat in positive and work out is positive. It is equation written in the positive sense. Heat in is positive, work out is in positive. But here it is given in the negative sense. So put the negative sign here. So it is minus Q dot out plus M dot I HI is equal to minus of W electrical in plus M dot E HE. Okay. Now put all this value. That means W electrical in plus MI HI is equal to Q dot out plus M dot EHE. Please balance it. Please balance it. Now beta, what is that? W dot minus Q dot is equal to, you have to take this, and there is a single inlet, single exit. There is a single inlet, single exit. So single inlet, single exit, M dot I is equal to M dot E is equal to M. This is the mass balance, okay? So here M dot into HE minus HI. HE minus HI. And that this is your air, and air act an ideal gas. So what is the change in enthalpy? Delta H is equal to Cp delta T. We know that for the ideal gas. For the ideal gas, we know that. For the delta H, so Cp T exit minus Ti. Cp T exit minus Ti. So here we have to write that W dot minus Q dot is equal to M dot Cp T exit minus Ti. Yes or not, beta? Now, the question is that we have to find the mass flow rate. Why? Because the volume flow rate is given. So ideal gas is ideal. Ideal gas. Apply the equation of state. PV is equal to MRT. If inlet it is given, so inlet condition it is given, beta. Inlet condition it is given. Okay, this is a mass flow rate. So put there is a volume flow rate, there is a mass flow rate. If you put this volume flow rate, there is a mass flow rate. So if you find the mass flow rate here, okay, inlet pressure it is given. Yes, inlet pressure is given. So all the things is given. So this is your Pi volume flow rate divided by R into Ti. Put all this value here. It is answer is 3 kg per second. Put all this value Pi. Very important information I am giving you, beta. Very important information. This is the equation. In that equation, pressure always kept in kilopascal. Very important. And temperature always kept in Kelvin. If you don't know, you are not qualified to 2024 exam. I'm telling you. If these things you don't know, you are not qualified to 2024 exam. Okay. So put this value. This is your 15 and this is your kilowatt. This is your electrical work. It is your electrical work is kilowatt and heat is watt. Very important. So this is 15. So this is 0.2. So this is 15. This is 0.2. Is equal to 3 into Cp air 1.005. Always remember. Exit temperature we don't know. Inlet temperature we have a 70. What is the exit temperature? 21.9 degrees centigrade. And Papaji, you are right, Manish. Manish, you are right. Clear? This question is clear? This question is clear. So simple application. Okay. So we have a good question. So this is first question is very good question. This is also very good question. Don't mind. But this question is straightforward, not very much logical. So we have to move the next question. This is a very important question. This is very important question. I'm telling you. Steady flow energy question. This is very important question. Please read this question. Please read this question. Okay. This is really very good problem. Please read this question, everyone. Yes, Manish. Same process. Yes, Manish. Same process. Okay. Same process it is. Very good. Without same process, you cannot do the solve. This is the read this question carefully. What is that? The temperature and pressure of air. Okay. What is this figure? Figure it is given. This is your nozzle. This is your nozzle, and this is your reservoir. Okay. This is your reservoir and this is your nozzle. The temperature and pressure of air in a large reservoir. Okay, there is a reservoir. In the reservoir, there is a device is attached. What is the device? This is it will explain in the question. So reservoir, that means what is reservoir? That means this is your inlet, 400 pascal and 3 bar respectively. A converging diverging nozzle. So this is your converging diverging nozzle of exit area, this is your exit area, okay? This nozzle exit area, it is given 0.005 meter cube, is fitted to the wall of the reservoir. So this is your reservoir and fitted it here, okay, in the reservoir. As shown in figure, the static pressure of the air at the exit section, the static pressure of the air at the exit section, that means at this portion, exit section. For the isentropic flow, this is very important, beta. This is isentropic flow, okay, through the nozzle is 50 kilopascal, okay, exit pressure. The characteristic gas constant and the ratio of specific heat. Characteristic gas constant is given R value, and this is Cp by Cv, that means a gamma value it is given respectively. The density of the air you have to find exit, that means rho at exit you have to find, okay. Second, the mass flow rate of the air through the nozzle, mass flow rate you have to find. This is a very good question and very common question while you are solving the T1 equal to T2. Why? Which question? T1 equal to T2. T1 equal to T2. What do you want, Manish? Okay. So this is your reservoir. Okay. This is your reservoir. On this reservoir, there is a converging diverging nozzle. 1 second. Okay, leave it. Converging diverging nozzle, you have to directly draw. I'm not drawing with the scale. Okay, this is like that. Okay, this is your inlet section and this is your exit section. Okay. Inlet section it is given beta Ti 400 Kelvin, Pi 3 bar. Okay, and what is the fluid it is there? Air. So air, the fluid is air. Finally we have to use the ideal gas equation. So convert this pressure into kilopascal, very important. This activity you have to do very smartly. Okay, so this is your 300 kilopascal. Okay, now exit area it is given. How much? Exit area it is given how much beta? Exit area at exit, how much it is given? 0.005. 1 second. Area at exit 0.005 meter square. Okay, and exit pressure it is given how much? 50 kilopascal. 50 kilopascal pressure it is given. Now R value it is given, gas constant value it is given 0.287 standard unit, kilojoule per kg Kelvin. Cp of the air it is given. If it not given, you can assume 1.005. So for simple calculation, we can assume 1 kilojoule per kg Kelvin. Gamma it is given 1.4. So these are the model of the question. Okay. Now what we have to do? First find it. What we have to do? Please beta. Now what is the steps? Everyone please. What is the steps now? What we have to find it? We have to find it. What is the exit density and what is the mass flow rate? So in this one there is a mass flow rate m dot. We have to find and exit density we have to find. How to start with this problem? If you don't know anything, first apply the steady flow energy equation. Why? Because this is an open system. Steady flow, nozzle, turbine, compressor, blower, pump, all these are devices are the steady flow. Apply the steady flow energy equation. Okay, apply the steady flow energy equation with the standardization. So steady flow energy equation for nozzle. Steady flow energy equation for nozzle. For nozzle. Steady flow energy equation for nozzle. What is the steady flow energy equation? If you don't know, calculate beta. Just with what is that? Q dot heat transfer rate of m dot. Why? Because we have to find mass flow rate. M dot HI CI square by 2 plus GZI is equal to W dot plus M dot E HE VE square by 2 plus GZE. Standard assumptions, we have to ignore kinetic energy change, potential energy change. Kinetic energy change, potential energy change. Right? Okay. Now, my dear, this is very important. Class 10 का है ना? हाँ, yes. Piyush, class 10. Yes, Piyush, that is the class 10. Class 10. You can solve. Piyush, better you can solve. Stay here 1 minute. It is a class 10. Okay, Piyush, solve this. No problem. If you are solved, you are very good. Okay, solve this. This is a class 10 problem. Now, now, my dear. So this is okay. Now, see here, the flow is isentropic. That means this is given flow. Flow isentropic. Isentropic, that means what, beta? For the isentropic flow, just you have to assume like that. Just you have to assume like that process must be adiabatic. See, adiabatic, reversible and irreversible. There are two things. If there is an adiabatic system, it may be reversible and irreversible. Adiabatic plus reversible must be isentropic. But isentropic need not be reversible adiabatic. Very clear. Need not be reversible adiabatic. Now, the second thing is that if we have to find the static, the question it is given that the static pressure it is given. Static pressure at the exit isentropically flow through that. Isentropically flow, yes. Yes, Rahul. Heat transfer is 0. Very good. Heat transfer is 0 isentropically. So in this question, the heat transfer is 0. Very good. Heat transfer is 0. So what is that now? M dot HI is equal to, and there is this is the nozzle. Nozzle has nozzle. There is a nozzle, and nozzle have no any working device. So work transfer is also 0 because it is a nozzle. It is a nozzle. Okay. So M dot HI. Now MEHE. That's it. Okay. Plus, my dear, if you write these things, neglect this kinetic energy at the exit. Danger mistake. Write down. Write down. Danger mistake. Write down danger mistake. Why? Because what is the purpose of nozzle? The purpose of nozzle to increase the kinetic energy at the exit, so you cannot ignore. That is the very important thing. If we neglect the kinetic energy at the exit, there is no purpose of the nozzle. So, you cannot ignore this one. Yes, the change in kinetic energy is 0. Why? Because this is horizontal. And if we find the exit kinetic energy maximum, there must be a minimum kinetic energy at the inlet. Why? Because that kinetic energy is converted into the exit kinetic energy maximum, so automatically the inlet kinetic energy is less as compared to exit. So it is not zero. It is not. So this value GZ1, this value and this value are equal. So it is cancel out. This is exist. Why it is exist? Why? Because it is a nozzle. Okay, but this kinetic energy, inlet kinetic energy is not zero. It is neglected as compared to exit. Very important. At compared to exit. So you have to neglect. So from here MEHE plus. So this is your MEHE VE square by 2. Yeah, V, yeah, C, you can say that V or C, no problem. Q dot is 0. CE square by 2. This is your energy. So here write CE, kinetic energy, CE square by 2. That is the very notable point, okay? Now, so this mass, exit mass or inlet mass are same. Why? Because one inlet, one exit. So mass flow rate at inlet, mass flow rate at exit is equal to mass flow rate. So these are the same. So what is that? HI minus HE is equal to VE square by 2. Now, there is an ideal gas. This is your ideal gas. So what is the change in enthalpy? Cp delta T. That means Cp T inlet minus T exit is equal to V at exit gas square by 2. Okay. Now my dear, Cp you have, Ti you have, Cp you have, Ti you have, exit velocity you don't have, and exit temperature you don't have. So from this equation, there is a one equation and two unknown. You cannot find anything. But you can use this equation furthermore. So this is your exit velocity. Now, what is the second step? How to handle? How to handle? Same idea. Very important, I'm telling you. See, for isentropic flow, for isentropic flow, number first, ideal gas. Ideal gas. You must have to use this relation. You know this. T exit, T inlet is equal to P exit, P inlet is equal to V inlet by V exit. Here it is your gamma minus 1. Here it is your gamma minus 1 upon gamma. Just remember this thing. Otherwise, no, don't use the ideal equation. If you use the ideal equation, there is no any meaning. Why you are using the ideal equation? From this ideal equation, what you have to do? Nothing you have to do. See, there is a pressure given, pressure inlet given, temperature inlet. So you have to find the volume at inlet. What do we mean if you find the volume at inlet? There is no any meaning. You have to find the inlet exit temperature first. So to finding the exit temperature, we must apply this equation. And very important thing, this is our assumption of this equation. You know these things. Okay, put this value on. So we have to take this to 1 to help out. So there is a exit temperature. What is the inlet temperature? 400. Exit pressure 50. Inlet pressure 300. Gamma 1.4 minus 1 divided by 1.4. So what is the exit temperature? 239.5 Kelvin. this is your exit temperature. Okay. Once you have to find the exit temperature, we can easily calculate the exit velocity. What is the exit velocity? Yes. What is that? 21.86. No. So this is your exit temperature in Kelvin. So what is the exit velocity here? Put this value. What is Cp? Cp, it is your, my dear, this is your kilojoule. One thing is very important here. 90% student gets mistake here. What is the mistake? Please tell me. See, what is this unit? What is this left side unit? What is this left side unit? Please tell me. What is this left side unit? You are right on. What is this left side unit? Kilojoule per kg Kelvin. Cp is kilojoule per kg Kelvin. This is Kelvin. So Kelvin, Kelvin cancel. So this unit is kilojoule per kg. What is the unit of this one? This is your meter square per second square. This is your meter square per second square. And meter square per second square is joule per kg. Joule per kg. So this is your kilo, this unit, see, this is your meter square per second, meter per second square. And meter square per second square unit is joule per kg. So this is your joule per kg and this is your kilojoule per kg. This is your kilojoule per kg, this is joule per kg. So convert this kilojoule per kg into joule per kg. So multiply 10 to the power 3. Very important. This is V square. So meter per second ka whole square. This is velocity. Meter square per second square. And meter per second ka whole square, the unit is joule per kg. And this is joule per kg and this is kilojoule per kg. So convert it to, so multiply 10 to the power 3. So this is your, what is that? This is your 1 cross 10 to the power 3. Exit temperature, it is your 400 inlet temperature. Exit temperature is 239.5 is equal to exit velocity divided by 2. So what is the exit velocity now? Exit velocity is 567.98 meter per second. Up to that, there is any problem, beta? Please, anyone? Manish, Rahul, Piyush, anything, beta? Any problem? Everyone, please. This is your exit velocity. Is there any problem in this one? So we have to find the exit velocity. So this is the kinematic, this is the fluid parameter. From the thermodynamics parameter, we have to find the fluid parameter. This is the beauty. This is your beauty. From the thermodynamics point of view, we have to calculate the fluid parameter. Okay, so this is your exit velocity. Once you have to find the exit velocity, why we have to multiply it? And this is very important. Why? Because this is your kilojoule. Don't miss it. Okay. Okay. So if you have exit velocity, apply ideal equation. PV is equal to MRT. Okay. So we have to write P. There is a density rho R into T. So we have to find exit. So P exit, density exit, R T exit. So here we have to find density at exit. P at exit, R T at exit. Put the value. P at exit is 50, R is 0.287, temperature at exit is your 239.5. So this is your 0.727 kg per meter cube. It is clear? It is clear? Yes or not? This is clear, beta. Density at exit. This is clear, density at exit. This is your density at exit, it's clear. Now, we have to find the mass flow rate. You have to find the mass flow rate. So, my dear, this is, see, the question it is saying that the mass flow rate of air through nozzle in kilojoule per kg second. So, we have to find the mass flow rate. And mass flow rate is constant. Yes or not? What is the mass? 0.728. Correct, Manish. So, what is the exit? What is that? Mass flow rate. We know that density is equal to mass flow rate into volume flow rate. And the mass flow rate is equal to, what is the volume flow rate? Area into velocity. Volume flow rate, area into velocity. Now, so from the mass flow rate, density, area into velocity. So, velocity, where you have to have a velocity information? Exit. So, velocity at exit. So, velocity at exit, density at exit, area at exit. So, this is a mass flow rate. Density at exit, just now we have to calculate 0.727. Area at exit, it is given with a 0.005. Velocity at exit, you have to already find velocity at exit. 567.98. 567.98. What is the value it is? 2.06 kg per second. Clear? Everyone? Clear? This is clear, beta? Everyone please tell me. This is clear, everyone please tell me, beta. This is clear? Please tell me. This is clear, beta? Everyone please tell me. This is clear, everyone please tell me. 2.004. Correct, Rahul. So, how is the question? How was the question? Please reply in the comment. That is the tough, moderate or easy. Please reply in the comment. This question is tough, moderate or easy. Please reply in the comment. This question is tough, moderate or easy. What do you think? This question is tough, moderate or easy. What do you think? Please reply in the comment box. This question is tough. Option A. Option B, moderate. Option C. No, not a good question. I am not asking like that. This question is tough, moderate or easy. Option C is easy. Option D, moderate. Very good. Very good, Manish. That is the very good option. Moderate question. It is not tough. So, my dear, you don't bother about while the preparation of the GATE examination, tough question. This is 4-mark question. There are 2. So don't bother about the tough question. Always bother about the moderate question. That moderate question is very important and very, very, very high chance to the upcoming GATE examination. Don't solve, please, I request to tough question. If that is tough, so tough is all. But the question is moderate, someone have faced difficulty in that question and someone can solve very easily. So the moderate question is very, very, very high chance to ask in the upcoming GATE exam. So try to always solve moderate question. Not very easy, not very tough. That is the good strategy of the preparation of the exam. Okay? Okay? Okay, beta. Now, so this is first question is your first law. This question is also for the first law but for the open system. Now we have to start the next question. Wow, this is very good question, and this question is related to the first law for the unsteady problem. First law for the unsteady flow problem. Unsteady flow problem. This question, please read this question. सर वेलोसिटी वाला मिस्टेक से हाँ that is a good see mistakes yes you are Rahul. I understand what you want to say that yes velocity that's why this is the moderate. Tough, it is not a tough question, beta. Get that what is the I am question selecting, that is not very tough question. That is the moderate. So that the question is aptitude based, where you have to chance the mistake. Rahul, you are right, beta. You are right. Okay, now you study this problem. This problem is a discharging problem. It is not charging, it is a discharging. Okay, so this is the unsteady flow problem. That means what is the parameter within the system that will change with respect to time. Okay, what is the question? Please read the question very carefully. What is the question, beta? Please read the question very carefully. An insulated, so this tank is insulated. There is no any chance to transfer the heat, and the volume of that tank is 8 meter cube. Rigid tank contains air at 600 kilopascal. Okay, and 400 Kelvin. Okay, a valve connected to the tank is now open. So this valve is now open for the discharge. Okay, open, and the air is allowed to escape. That means what is the flow of air that will be allowed to escape into from the control volume until the pressure inside drop is 200. So up to what level the fluid will escape? At a pressure 200 kilopascal. That means the air temperature during the process is maintained constant. So what is that means each and every time, that means what is when the fluid is flowing outside from this control volume to outside, the property will change, but the temperature property, in that property, one of the property is temperature, and that temperature we have to fix according to question. How to fix the temperature? By supplying the electrical work, so that if there is a discharging, it must be a temperature drop. It is very damn sure. If the discharging is there, that is the very good interview question. Someone asks you, if the discharging of the gas, why the temperature of the tank is dropped? That is the very good question of the interview. Please find it in the textbook. Okay. So if the discharging is there, the temperature is dropped. But according to the question, they says that the temperature is fixed. When the temperature is fixed, when you are continuously heating. So there is a heating device is there. The air temperature during the process is maintained constant. That was temperature maintained constant. How to maintain constant? Why the electrical resistance heater placed in the tank. Okay, determine the electrical energy supplied to the air during the process. That means we have to find this electrical work. We have to find this electrical work. Clear? And mind it, beta, this question is very, very high chance in the gate. This type of question. Very high chance. So this question related to charging and discharging, let's solve. So question is clear. Now the gas constant it is given. The gas constant it is given. Okay. Question is clear, beta? Now we have to start the problem. Rahul, Manish, please try to solve. Please try to solve. See, what is that? I am solving this problem. See, my dear, one thing is very, I given the, many students says that sir, discharging, charging, that means unsteady flow problem is very little bit tough. No, it is very easy as compared to all the topic related to the thermodynamics. How? But the process you have to must be a fix the process. Process is very fixed. What is that? See, during the control volume analysis, please listen carefully here. Please listen very carefully. During the control volume analysis, inlet something, exit something. During that, the property within the system, that means system property will change. So there are four notation. One is I, exit, inlet, other is exit, and third one is state point 1 of the system, and second 2 is the state point 2 of the system. How? Let's suppose. Let's see with that. So we have to, so there is I, E, 1, 2. There are 4 notation. This 2 notation is for the section, at the section, cross section, and this 1 and 2 notation is for the system. I will give the example very simple. If there is a pipe, okay, mass and energy balance, but notation is very important. Mass and energy balance, yes. Let's suppose this is our control volume. This is our control volume. So something is in, so there is I. Something is exit, so there is exit. While entering and exit, its property will change from point 1 to point 2. While unsteady. That means inlet, this is your inlet, this is your exit. While entry and exit, the property of the system will change from point 1 to point 2. Work is your. My dear Manish and Rahul, I give you a challenge. You cannot solve this problem. I am telling you, you cannot solve. I am telling you, you cannot solve. Even your teacher, you cannot solve this problem. Even your teacher, yeah, where you have to teach, study that one, they cannot solve this question. So please don't try. I know that you cannot solve. It is not charging, it is a discharging. So discharging have a different method as compared to charging. 90% teacher always try to solve the problem of a charging. That means fluid which is come in. The fluid which is come in. This is fluid which is come out. Mind it. So little bit change. You cannot solve, I am telling you. It is not demotivated statement. It is a statement that it is a very good question. 99% of teacher only solve discharging. That means something is in. But this question is something is out. That is the beauty. That is the beauty. Okay? Okay, beta? That is the beauty. Wrong. 840 watt. Wrong, beta. That is wrong. Rahul, wrong. Manish, wrong. Clear? No, it is not like that. Okay? Now, so that is the clear thing. Ki, sir, in this question we have to note it 4. Now, now we have to solve this problem very, very consciously. And please try to see. This is only one platform where you have to see this problem only for discharging. And very easy manner, very easy, very easy, very easy, very easy. I'm telling you. So, my dear, if you have a control volume with unsteady state, this is your exit section. Yes or not? This is your exit section. Yes or not? This is your exit section. It is visible? Yes. This is your exit section. I. This is your exit section. There is no any inlet. That means in the sense of mass. There is no any inlet mass is there. So first, according to the mass, we have to take inlet exit. So here in this question, there is state 1. Then state 2. Then section I. Then section 2. Section E. This 4.7. 4.7. No, wrong. Wrong. State point 1, state point 2. This is within the system. Section 1, inlet to the system. This is exit system. So there is a no any exit. So there is a no any inlet. That means this is 0. That means inlet mass Mi, it is your 0. There is no any inlet. Only exit is there. What is the state point 1? P1, it is given 600 kilopascal. T1, it is given 400 Kelvin. State 2, P2, it is your 200 kilopascal. And according to question, T2 is equal to T1 is equal to 400 Kelvin. It is given. It is given. Okay. This is the question. Now, what is the mass balance? What is the mass balance, beta? First, balance the mass. Mass. What is the mass balance? Mi, M exit, M2 minus M1. M2 minus M1. Okay. There is no any inlet mass. Why? Because this is a discharging. Why? Why? Because this case is only discharging. Only discharging. Only discharging. Okay. So what is the exit mass? Is equal to M1 minus M2. This is clear? This is your exit mass. So what is the exit? 31 point? No, it is wrong. 31 in exit section, it is your that means exit mass, it is your M1 minus M2. Okay? Okay. Now, second one is the energy balance. Now, my dear, what is the energy balance for the unsteady flow problem? That is a very important. This is a very important. Energy balance, we have to write. Energy balance. And this is for unsteady flow problem. Unsteady flow. This is unsteady flow. So energy balance for the unsteady flow. What is that? Q dot plus Mi Hi Ci square by 2 plus Gzi is equal to change in internal energy 38.4. 38.4 wrong. 38.4 wrong. Change in internal energy. That means this is your within the system M2 U2 plus C2 square by 2 plus Gz2 minus M1 U1 plus C1 square by 2 plus Gz1. So this is change in internal energy plus exit mass M dot exit He plus Ce square by 2 plus Gze plus work transfer. You know this relation? You know that? Everyone please. Manish, Rahul, everyone please. You know this equation? You know this equation? See, this term come into picture when there is a unsteady. In the case of steady, this is 0. This you know, please tell me beta. This you know, everyone please tell me. This is important. This term M2 minus M1. Yes, Rahul, very good. Thank you. If you know, I am very happy. If you know, I am very happy. So this is your change in internal energy. This is for the exit and inlet. Clear? Very good, very good. Now, in the question that says that this is insulated, so this is 0. This is 0. Here we cannot take work is 0. Why? Because there is a electrical work is there. So you cannot take. But there is no any information of kinetic energy and potential energy. So you can take hand. And there is no any inlet. So inlet mass is 0. So this Mi it is 0. So all the term it is 0. Okay, Mi is 0. Now M2 is there. But there is no any kinetic energy, there is potential energy, kinetic energy, potential energy, kinetic energy, potential. You can neglect it. That is system is stationary. Now, so what is the equation? M2U2 minus M1U1 plus MEHE plus W dot. This is your equation. So if your equation is correct, that is all these things is correct. What is this one? What we have to put from here? Electrical work. This is work in. We have to write it is all in positive sense. But in the question there is electrical work in. So put here minus of W electrical. Why? Because it is in. Now you have to write the equation. So if you write the equation, what is the equation? M2, this is M2U2. M2U2 minus M1U1 plus MEHE minus W electrical. It is 0. This is equation, yes or not? This is equation. Now, so what is here? We have to arrange something. Yeah, you can take like that. So this is your steady. This is your unsteady flow energy equation. Okay, why there is a negative? Why? Because electrical work in. Gautam says that, sir, you explain why inlet mass is 0. Arey lapar ganju. See, why? There is no any inlet. This problem is for discharging. This problem is for discharging, my dear. Clear, Gautam? Gautam, clear, beta? Please reply. This is discharging, not charging. So there is no any inlet mass. There is nothing is in the sense of mass. So inlet it is 0. Gautam, right, beta? Understood? Very simple. Okay. So this is your mass. Now, my dear, the real picture come. Now, how to find U2, how to find U1, how to find enthalpy exit. This is very important, I'm telling you. Why? Because this is given. Electrical work input it is given. Now, first of all, to putting all this value of this equation, we don't have an initial mass and we don't have a initial mass of the system and final mass of the system. Thank you, Gautam. Initial mass of the system and final mass of the system there is not given. So first find inlet mass, initial mass of the system and final mass of the system, multiply it, that is your mass of the discharge. So how to find M1 and M2? Please comment anyone. Anyone comment how to find M1 and M2 in initial mass of the system and final mass of the system. How to find? Please comment anyone. Please comment anyone. Right. Right, Rahul. Right. Very good. Very good, Rahul. Here enthalpy we have to take average. That is very important thing. Very good, Rahul. I am very happy. But think why we have to take average. Please think. Please think. Okay. So how to find M1 and M2 in the ideal case. Very good. Ideal. Rahul. Very good. Rahul, you are very intelligent. So So now to find M1 and M2, inlet and not inlet, initial. Initial and final mass of air in the tank. In the tank, we have to find. Please find it. What is the M1? P1 V1 by R T1. What is the value, beta? Please tell me. M2 P2 V2 by R T2. My dear, very good, Rahul. So this V1 and V2 are same. Why? Because the tank is rigid. See, rigid tank. Tank is rigid, so volume is same, doesn't change. Okay. So V1 it is your how much? 41.82 and 30. No. M2 is wrong, beta. M2 is wrong. Rahul, M1 is correct. M1 is 41.81 kg. M2 is wrong. Rahul, please check M2. M2 it is 13.94 kg. Please check it, Rahul. So this is your initial and final mass of the tank. Rahul, please check M2. Okay. So once you have M1, M2, so you have exit mass. What is the exit mass? 27.87 kg. 27.8 kg. Now you have all this M1 you have, M2 you have, ME you have. 13.9. Right. So what is the electrical work here? So W electrical is equal to MEHE plus M2U2 minus M1U1. Just you have to take this side. Now, what is ME? ME is 27.87 into HE. Okay. Plus M2 is how much? 13.94 into U2 minus M1 41.81 U1. Now the question is come, how to find U1, U2, HE, HI? Okay. How to find U1 and U2, beta? First find U1 and U2. See my dear. First tell me, is there internal energy change? Okay, Manish. Okay, no problem. Now, my dear, first tell me, Rahul, Manish, everyone, please, everyone, Rocky, everyone, please see. Is there internal energy change? Please tell me. Is there U1 and U2 are same or differ? Before calculating, I am asking. Before calculation, I want to ask, is there U1 and U2 are same or differ? Please tell me. Please tell me, is there U1 and U2 are same or differ? Option A, differ. Option B, same. Option D, I don't know. What yes? What yes? Rahul, the same or differ? Please tell me. Same. Yes. Manish, you are right. Why? Because this is for the ideal gas, and ideal gas is the function of temperature, and inlet and exit temperature, initial temperature of the system and final temperature of the system is same. Why? Because we are the resisting. Yes, very good. So U1 is equal to U2 is equal to CV into T. Okay. Now, how to find CV? CV is equal to R by gamma minus 1. We know that, this relation, basics relation. So, R it is given 0.287, gamma value given 1.4 minus 1. So, CV it is your 0.7175 kilojoule per kg Kelvin. Okay. Now, put the value, that means here U1 is equal to U2, CV is 0.7175 and T it is given. How much T it is given, beta? 400 into 400. If you multiply this value, it is 287 kilojoule per kg. That's it. So this is U1 and U2. Clear? Not CP, beta, CV. U is equal to CV. Rahul, not CP. U1 equal to U2, not CP. CV into T. If there is a H1 equal to H2, there is a CP into T. Little bit mistake. Okay, Rahul, this is CV, not CP. Clear na? Okay. So this is your U1 equal to U2. Okay, now, my dear, the question is come how to find HE, exit enthalpy. This is very important thing. How to find exit enthalpy? 287, correct. See, my dear, if there is a tank, and there is a valve, something is discharging. Okay, this is our exit section. Let's suppose this is our exit section. Okay. Now, my dear, this exit section continuously changing. This exit section is continuously changing. So, under what? Why? Because enthalpy, internal energy, these are the function of temperature. Okay. Temperature at point 1 is equal to temperature at point 2. That means what is the temperature initially of the system is equal to temperature at final of the system. So there is no any problem in internal energy. But the enthalpy at the exit and at the exit condition, temperature continuously changing. So on what temperature the exit enthalpy you have to calculate? You don't know. You don't know at what enthalpy and internal energy is the function of temperature of an ideal gas. So system temperature, initial system temperature and final system temperature is same. So internal energy is same, you can calculate it. But the exit section, the temperature is, why? Because these are the variable. You are varying the wall. So exit condition is varying. So exit condition is varying, that means exit temperature is varying. So at what temperature you have to calculate the exit enthalpy? You don't know. So you have to average it. So the exit enthalpy, it is your exit enthalpy at temperature T1 plus exit enthalpy at temperature T2 divided by 2. Now, exit enthalpy at what temperature is same? T1 and T1. Thank you, Vipin. T1 and T2 temperature is same. Now T1 and T2 temperature is same that means at this point T1 temperature, that means T1 and T1 temperature same. So this exit enthalpy at T1 and this exit enthalpy at T2 are same. But during the T1 and T2, this exit enthalpy will change. So we have to take average. Very important. Exit enthalpy at T1 is fixed. Why? Because T1 is fixed. Exit enthalpy at T2 is fixed. Why? Because T2 is fixed. T1 equal to T2. So this exit enthalpy of T1 and exit enthalpy of T2 are same. But during T1 and T2 are different, so we have to take average. Understood or not? This is very important concept. I am telling you. Never found this type of concept on any YouTube channel. I'm telling you, this is my challenge. So this you are, so at this one and this one, that means H exit at T1 is exactly equal to H exit at T2. Why? Because T1 and T2 are fixed, both are same. So these are same. So we have to put this value. This is what? That means this is your Cp into T. Cp into T. And what is the Cp? You have a Cp. Why? Because Cp minus Cv is equal to R. You have R. So put this value Cp and Cv. So Cp. So Cp is equal to Cv minus R into T. Put this value. Find the answer. This is your 401 401.8 kilojoule per kg. Kilojoule per kg. This is your He. Everyone please tell me. It is clear? Everyone please tell me. It is clear. The ball. Everyone it is clear. Please tell me. I am requesting you. This is very important thing. Never found in another YouTube. This is clear or not? Please tell me. This is clear or not? Please tell me. Why? Because T1 is fixed now. T2 is fixed. T1 and between T1 and 2 it will change. So it will take average. So divide with this one. So this is your, to divide, no, this is your, I think, plus 273. So this is your average. Oh, so it will take average. 1 second. So this is your divided by 2. 1.05. If you find, so this is not 1.05. This is this value. 1 second, beta. 1 second. Writing mistake is there. It is not this value. Writing mistake. How to calculate? This will calculate. So if you calculate this one, so it is your 2 into this one. 401.8. This is 20. So if you put this value, this is a 401.8 kilojoule per kg. Just calculate. You have a Cp, you have a T, just calculate. Okay, this is not a matter. So exit temperature. Now put all this value here. If you put all these values U1, U2, U, so this is your 3200 kilojoule. But the answer it is in kilowatt. So how to find joule into kilowatt? So you know that 1 kilowatt hour it is asking. Why? Because why we have to find the electrical in kilowatt hour? Why? Because what is the unit coming in your house electricity bill? That electricity bill is kilowatt hour. So in this question they are asking W electrical, that means electricity bill they are asking. And generally electricity bill it is in kilowatt hour. So 1 kilowatt hour, always remember 1 kilowatt hour it is equal to 3600 kilojoule. 3600 kilojoule. So just divide it. So if you divide it, this is your 0.889 kilowatt hour. This is clear, beta? Everyone please tell me. Manish, Rahul, everyone please tell me. This is clear? Everyone please tell me. This is clear or not? Please tell me, beta. Everyone, this is clear or not? Please tell me. This is clear or not? Please tell me. If it is clear, 0.889, correct. 0.889, correct, kilowatt hour. Clear? So, please tell me, this question is tough, moderate or easy? This question is tough, moderate or easy? This is your option. This question is tough, moderate or easy? Please tell me. This question is tough, moderate or easy? This question is tough, moderate or easy? Everyone please reply in the comment box. Please reply the comment box. This question is tough, moderate, or easy. This question is tough, moderate, or easy. Please reply, everyone. Yes. Very good, Rahul. This question not. Manish, Papa, not moderate. This is tough question. So only you people are solved. Other one not solving. Rahul, you are right. This is tough question. This is a tough question. Really. Not moderate. Manish, it is not moderate. So what is the advantage? Only you people you can solve. Okay? Why? Because there is a lots of mistake here. Okay? So this is tough question. So sometime tough, sometime moderate, sometime easy, tough, moderate, easy, tough, moderate, easy. Why? Because the examiner want to give you the fatigue load in your mind. So you can fail within the endurance limit. So that we have to design a endurance thing. Okay. So we have to design an endurance so that we are not supposed to be withstand much more as compared to the, so that the fatigue load we are not going within the endurance limit. So the our material is not fail. So if you design the material within the endurance limit, material we cannot fail. So though there is a fatigue load moderately, we have to design within the endurance limit. Okay. Correct. Correct. Now, so move forward. The next question. The next question is this one. Please try to solve. Please try to solve this question. Please try to solve this question, beta. An insulated vertical piston cylinder device. See, there is also, this is now charging. That's right. Right, Rahul. So this is your charging, okay? Previously this is a discharging, now this is your charging, okay? Please read the question carefully. An insulated vertical piston cylinder device initially contained, that means what is the initial? Is 0.1 meter cube of air at 150 kilopascal and 22 degrees centigrade. At this state, a linear spring touch the piston but exerts no force, only touching is there. The cylinder is cylinder is connected by a valve. So there is a valve to a line that supply air at 700 kilopascal and 22 degrees centigrade. The valve is opened and the valve is open so that the air from the high pressure line is allowed to enter to the cylinder. The valve is turned off when the pressure inside the cylinder reaches 600 kilopascal. If the enclosed volume inside the cylinder is doubling, that means up to what level you have to charging this piston, you have to charging this cylinder, you have to charging this cylinder up to the volume is double. Determine the mass of air that entered to the cylinder and the final temperature of air inside the cylinder. Mass of the air that enter into the cylinder, how much the mass, that means ME, and also find the final temperature of the air inside. Clear? Question is clear, beta? Everyone please. Question is clear, everyone please. Reply in the comment box. Question is clear? Okay. Now we have to start this problem. Okay. What is given here? So that is the tank, spring is there. Now they are asking that So state 1, state 2, section I, section E. Okay. So in this question, this is only charging. This is only charging. So there is no any exit mass. So exit section is 0. Why? Because charging. This is charging. So mass at exit is equal to 0. This is the first thing. Now, section I. This is your section I. Section I, it is given PI and TI. PI is 700 kilopascal and 22. 700 and 22. So I. PI 700 kilopascal and TI 22 degree centigrade, na? 22 degree centigrade. Clear? This is your PI, section I. Now, there is MI is also there. Now, state 1. State 1, volume is given, VI is 0.11 meter cube. State 1, the initial pressure 150 kilopascal. State 1 temperature, it is your also 22 degrees centigrade. What is the inlet temperature from the pipe is the same as the initial temperature. That means, what is the fluid temperature? What is the fluid temperature which is enter is the same the temperature which is at inside the tank. Okay, so Ti is equal to T1 is equal to Ti. State 2, V2 is double. That means V2 is 2V1. It is given. Yes or no? V2 is equal to 2V1. It is given in the problem. Now, what they given? Okay. We have M2. Now, what is the mass balance, beta? What is the mass balance? So, Mi is equal to M2 minus M1, yes or not? Okay. Now, we have to find initial mass. That means M1. We have to find M1. What is, why, how to find M1? Pi P1 V1 by R T1. Put all this value. What is that, beta? P150. V1 is 0.11. R is 0.287. Temperature is temperature is how much, beta? 22. 22 plus 273. 295. 295. How much it is? It is approximately 0.195 kg. So this is your M1. It is clear, beta? Please calculate, everyone. This is your M1. Okay. Now we have to calculate M2. So M2 is equal to P2 V2 by R T2. We don't have a T2 value. 0.195. Clear? Rahul, it is clear. Now we don't have a T2. So it is in the form of T2. So what is P2? P2 you have. P2 you have. Final pressure, it is in the side cylinder. They say that the cylinder is connected by the valve to a line that supply air 700 kilopascal and 22. That means 700 kilopascal P2, and the valve is open and air from high pressure allows to enter the cylinder. The valve is turned off when the pressure inside the cylinder is 600. That means this is a P2. Up to what level the pressure inside? 600 kilopascal. So this is your P2. So P2 is your 600. V2 is 2 V1. You have 0.22 divided by 0.287 into, you don't have a T2. So if you calculate this value, this is your 459.303 divided by T2. This is your M2. This is your M2. Now, so what is Mi? What is Mi, beta? So Mi is equal to M2 is 459.303 divided by T2 minus M1 is 0.195. This is your Mi. This is your Mi. Okay. Now we have to find T2 temperature. We have to find the T2 temperature. So that we have to find Mi. And then what they are asking? They are asking that the mass of the air that is entered in the cylinder. That means Mi. They are asking Mi entered in the cylinder. Mi. So to find Mi, first you have to find T2. To finding the T2 temperature, you have to apply the energy equation. Energy equation. What is the energy equation? You know that energy equation for unsteady flow. What is that, beta? Q dot plus Mi Hi plus Ci square by 2 plus Gzi is equal to M2 U2 plus C2 square by 2 plus Gz2 minus M1 U1 plus C1 square by 2 plus Gz1 plus Me, right, dot, no problem, dot Me He plus Ce square by 2 plus Gze plus work. Okay. Now there is insulated, so this is 0. There is no any kinetic potential, kinetic potential, kinetic potential, kinetic potential. Now there is no any also exit, so this is 0, no problem. This exit mass is 0, so all terms is 0. Now work is not 0. This beta not 0. Not 0. Why? Please tell me, the work is not 0. Why? Please tell me, beta. Rahul, Manish, please tell me why the work is not 0 here? Why the work is not 0 here? Please tell me. And which type of work is here? Which type of the work is here? Which type of work is here? See, if the fluid is entering, the fluid boundary will displaced. If the fluid is, why? Because this is a rigid, this is a fixed boundary, this is fixed boundary, this is fixed boundary. Yes, but this is the moving boundary. This is your moving boundary. This moving boundary is expand. So if the moving boundary will expand, spring will do the work on the moving boundary. So there must be a spring work. What is the spring work? It is a linear. Yes, it is variation. Yes, sir, variation. So linear variation. Linear variation. Spring work is the linear variation. So there is a trapezium. That means this is like that. This is wiring like that. Trapezium. So this work. So if there is a P and there is a V, so P1 plus P2 half. So what is the area? Half P1 plus P2 into V2 minus V1. You know this thing? This is spring work. You know this thing, everyone please? Manish? Everyone please? P1 plus P2, V2 minus V1. This is your spring work. You know this thing? Rahul, you know this thing? P1 plus P2 into V2 minus V1. These are the variation. Spring work. This is the spring work, okay? Half. This is a trapezium. So this is the area of the trapezium. Okay. Now, so what is the equation here now? M dot I H I minus, this is your boundary work, is equal to M2 U2 dot plus M dot 1 U1. Okay. So this is your MIHI is equal to M2 U2 plus M1 U1 plus boundary work. Okay, put all this value. So MI, what is HI? CPTI. What is M2 is there? What is U2? CVT2 plus M1. What is U1? CVT1 plus boundary work. This is there. This is there. Now, MI is there, M2 is there, M1 is there. Put all this value. Put all this value beta. I'm putting this value, no problem. I will put this value. So, MI. What is MI here? MI is 459.303 divided by T2 minus 0.195. Put MI. So this is your 459.9303 divided by T2 minus 0.193. So this is your MI into CP. Let's suppose CP take 1, no problem. Into T1 295. So this is this value. Okay, is equal to M2. M2 is what? This is your M2. M2 is what? 459.303 divided by T2. Put this value. 459.9303 divided by T2 into 0.718 CV into T2. So this is okay. This is done. Now plus. So this is minus here. This is here minus now. So this is minus U2 minus M1 U1. This is minus. Minus 0.195 into 0.718 into 293. This is this value. If you calculate the boundary work, that means spring work. So boundary work is equal to half P1 plus P2 V2 minus V1. Put all this value. This is your 41.25 kilojoule per kg. Kilojoule per kg. Put this value plus 41.25. Now this T2 cancel out. From here you can find T2. So if you find T2, this is your 351 Kelvin. This is your T2. This is your T2. This is your T2. Now, so this is your T2. So then question, what are they asking? Yes, this is final one. So mass of the air which is enter. Now once you have to T2, just put the value here, reverse back. Put the value here, reverse back. And find the mass. So if you put this value, this is 1.115 kg. That's it. So this is the mass which is enter, and this is the temperature, final temperature of the state. It is clear with everyone? This is the final state of the system. This is the final state of the system, that was T2 temperature. So how to find what is the condition? So this is a simple logic. If this is a question, so simple logic. First find M1, first find M2. What is the relation? So exit is 0. Now once apply the unsteady flow energy equation, so balance it. Now mind it, here the boundary work is 0. The boundary work, it is nothing, it is the spring work, and spring work, it is what the area under the trapezium, and area under the trapezium is equal to half P1 plus P2 into V2 minus P1. Put the value here, all the calculation, and do this one. This is clear? So this is T2, put the reverse back in T2, this is the mass. Clear everyone? So this is the lengthy problem, but you have to try to practice like that. This is a little bit lengthy, but there is all of things, you know that one. Okay? Now we have to start the next problem. The next problem is your, yes. This is for the second law. This problem related to the second law. This problem is related. Please read this question, beta, carefully. Please read this question carefully. Please read this question carefully. Yes, please read this question carefully. What is that behind the question? The question says that this question says that it is proposed that a solar energy is used to warm a large collector plate. We have to, that means this is your solar energy system in which we have to warm the air, used to warm the large plate, collector plate. In that collector plate there is a water is there. The energy would in turns to transfer as heat to the fluid within a heat engine. So there is a heat engine concept, and the engine would reject energy as heat to atmosphere. That means engine must be, this is a Kelvin Planck statement, atmosphere. Experiments indicate that during the experiment we have to found that 1880 kilojoule per meter square hour of energy can be collected. This will collected when the plate is operating at 90 degrees centigrade. That means in that plate the fluid is flowing and the fluid is at a 90 degrees centigrade. During that the plate will collect the energy 1880 kilojoule per meter square hour. Estimate the minimum area. That means as a designer engineer, if you have to install, someone says that, sir, I want to install my roof a solar plate collector. So what they want, that we want that minimum to minimum collector which have a maximum to maximum efficiency. So minimum collector area that would be required for the plant producing 1 kilowatt of useful shaft power. The atmospheric temperature may be assumed to be 20 degree centigrade. Clear? Now we have to solve this problem. So there is a collector plate. There is a plate collector. So this is your collector plate, beta. This is your collector plate. Okay, this is your plate. And not this one. This plate is little bit inclined. You know that the plate, solar panel plate, it is little bit inclined. So we make this little bit inclined, no problem. Oh, it is not done, no problem. Take like that. Okay. This is your plate, solar plate. Okay. This is solar plate in which the fluid is flowing. And this plate from this is sun. This is your sun. This is your sun. From this sun, this plate takes the energy. This plate takes the energy, and in this plate, the fluid is flowing. Okay. This is solar. And this takes the radiation energy. This takes the energy in the form of radiation, and this is your collector plate. This is your collector plate. This collector plate of a temperature 90 plus 273, that means this is your 363 Kelvin. Okay, it will take a heat, that means it will take a energy. Let's suppose this is your QH. This energy is supplied to the heat engine. This heat engine produces a net work output and dump to the remaining heat to the atmosphere. Okay, so this is a high temperature. This cycle, this is a heat engine cycle called clockwise direction. Now the question is coming in the mind. So now, my dear, the first question is that this heat, that means this heat will reject. It is given in the question. The heat will accept by this one is 1880 kilojoule per meter square hour. It is given in the question. Okay, this is the data value. It is given in the question. Okay, no problem at all. Now, my dear, we find the minimum area of this collector. What is the minimum area? And the net work is 1 kilowatt. This is your 1 kilowatt work will produce. It is in the question. Now, my dear, what is this cycle? It is a reversible cycle or what? It is a reversible cycle or what? Please tell me. This heat engine working on a reversible cycle or what? Please think. Please think with a to find. What you have to find? To find minimum collected area. Minimum collector area, A minimum. Please tell me. Hi, Q is equal to U plus W. What do you have to find? From this one? No. First, give me a reply whether this heat engine is reversible or irreversible for the minimum area. If you assume, if you design, question lengthy है ना, question not lengthy. Question lengthy नहीं है. One line question, one line solution. I am asking that. Please focus what I want to ask you. We have to design as an engineer minimum collector plate. So for the minimum collector plate, whether we have to design heat engine reversible or irreversible. This is my question. Please tell me. If we design the minimum collector plate, if you design the plate area is minimum, whether we have to assume this heat engine is reversible. How? How to assume like that? See, reversible. How? Why we have to assume the reversible? See, this is the logic. Just I give. No one can give this reply. Okay. See, since area is minimum, yes or not? Minimum. So area, if this area is minimum, what is QH? What is QH? This is minimum. Yes or not? This is minimum. This is minimum. By radiation. So, see, this is Q radiation now. This is radiation. If area is minimum, this heat which is radiated by the collector plate is minimum. Yes or not? If we design the minimum area, what is the solar energy? What is the energy which it will collect by the plate is also minimum. So if this is a minimum, so this is a minimum. Now, by radiation. Now, my dear, as we know that, what is the efficiency? W net by heat supply. W net by heat supply. What is the heat supply minimum? So if this is fixed, that means we want this is fixed. This is fixed. Why? Because this is fixed, no changing. So if it is fixed and if you design the minimum area, this is minimum, this radiation is minimum. Why? Because this area is minimum. So QH is minimum. So if QH minimum, the efficiency is maximum. So if you design the heat engine which have a maximum efficiency, that must be a reversible heat engine. Yes or no? Please tell me. That means this heat engine must be a reversible heat engine. Please tell me. You know this thing previously? Please tell me. Please tell me very truly, Rahul, Manish, everyone, you know this thing logic? Just now what I have to discuss before one minute? You know this thing? Please tell me, reply in the chat box. Truly. You know this thing? What is the logic? What is the logic? You know this thing? Why we have to design this engine as a minimum reversible? No, I know that. Manish, Papa, you know this thing? Please reply in the comment box. I want, yes. So this is the logic, my dear. This is the things you have to know. It is not things that anything is truly. No. How to draw? No one book, no any other source who can tell you this fact. Under what condition? Why? Because see, area, what is the radiation? Radiation or a convection, anything depends upon the area. What is the radiation? Epsilon A into T4. You know that in the form of flux. So if we want that area minimum, the radiation is minimum. And this heat will transfer due to the convection mode. Why? Because fluid is... And what is the convection heat transfer? HA delta T. So also there is area. So if the area is minimum, heat transfer is minimum. So if the heat transfer is minimum, we must have a design a heat engine of a maximum. So the maximum heat engine, if you design a maximum efficiency heat engine, we assume that this heat engine operate on a reversible cycle. Clear? Clear? Yes or not? This is clear, beta. That's why this all are the logic. Okay, now? Right. Now the question is very simple. Now the question is, why I am taking this question? Why? Because everywhere they are missing. This is missing. This type of the logic is missing. So that I will take this question. Now, what is the heat engine maximum efficiency? Heat engine maximum or irreversible, we know that TH minus TL divided by TH. Put this value, I've got TH, TL, all this value you have. So this is your 0.192. And what is the efficiency? We know that W net by heat supply. W net by heat supply. Now, what is this heat? What is this QH beta? W net you have. W net you have. Put this value. Find QH. So here QH is equal to. What is the value of QH beta here? QH is equal to 5.21 kilowatt. 5.21 kilowatt. That means if you design this plate of a minimum area, the heat engine will extract the heat by 5.21 kilowatt. This is your kilowatt, but this is given 1888 kilojoule per meter square hour. Yes, 5.21 kilowatt. Now, my dear, if we convert this kilowatt, into kilojoule per hour, please convert it is in. This is your kilowatt. This is your kilowatt. I want to convert into kilojoule per hour. How much it is? Please reply in the comment, beta. Rahul. This is 5.21. We want that kilojoule per hour. How much it is? How much it is? Why? Because this is kilojoule per hour it is given. How much it is? How much it is? Please tell me. This is your kilojoule per second. This is your kilojoule per second. Kilowatt is what? Kilowatt is what? Kilowatt is your kilojoule per second. But we want kilojoule per hour. No, 1 point. No. This is your approximately 1880 kilojoule per hour. Multiply with the 3600 na, Rahul. This is kilojoule per second na. We want kilojoule per hour. So multiply with 3600 na. 1 second. 1 second. 1 second is how much? 1 by 3600 hour na. So that 3600 hour multiply with this one na. Rahul, why you are mistake yaar? You are very intelligent. Don't mistake. It is clear now? It is clear? Ha. So 18800 kilojoule hour. Now, now my dear. So please see this one. That means, see, since 1880 kilojoule per hour, how much area is required? Please tell me. How much area is required? Yes, 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 Manish. Right. That means, yes. See, 1880 kilojoule per hour required 1 meter square area. Yes or no? This is in question. 1880 kilojoule per hour required 1 meter square area. This is given. Required 1 meter square. This is given. So 1 kilojoule per hour required 1 divided by 1880 meter square. Now, how much heat will extracted kilojoule per hour? So we have to find this basis. Why? Because on this basis the area is minimum. So 18800 kilojoule, 18800 kilojoule hour required. 18800 divided by 1880, that means approximately 10 meter square. Clear? Clear everyone, please tell me. This is clear? This is clear everyone, please tell me. This is clear everyone, please tell me beta. This is clear? This is clear everyone, please tell me. This is clear or not everyone? Yes, 10. Yes, 10. This is clear? So 10 meter square area is required. Clear beta? Okay. So now we have to go through the next problem. Now, this question. So second law question, engine related, finish. Now this question related to the entropy balance, entropy chapter. Read this question carefully. Consider steady state heat transfer through a 5 meter cross 6 meter bricks wall of house of thickness 30 centimeter. On a day when the temperature of the outdoor is 0 degree centigrade, the house is maintained at 27 degree centigrade. The temperature of the inner and outer surface of the bricks, that means inner and outer surface of the bricks, is 20 degree centigrade and 5 degree centigrade respectively. The rate of heat transfer through the wall is 1035 watt. Determine the rate of entropy generation in the wall, very important, and the rate of total entropy generation associated with this heat transfer. That means heat generation within the wall and the total heat generation. Clear? Question is clear, beta, everyone, please. Question is clear, everyone, please. Question is clear? Okay. Okay. So, my dear, see, I will discuss complete things for this one. Why? Because this is related to very good concept. Okay, what is that? See. So this is your bricks. Okay. This is your bricks. Now, this bricks have this length is 30 centimeter. This is your 30 centimeter. Okay, this length is 30 centimeter. Now, heat will enter. The heat is entering. The heat is entered from this phase to this phase. This heat will enter. Okay. This heat will enter. Okay. This heat will enter. Clear. Okay, beta? Now, that means this is your inside and this is your outside. That means this is your inside and this is your outside. Okay? Okay? This inside temperature, it is given 27 degrees centigrade, and this outside temperature, it is given 0 degrees centigrade. This inner wall surface temperature, it is given 20 degrees centigrade. The outer wall temperature, it is given 5 degrees centigrade. Okay. Now, my dear, heat will transfer from this point to this point, convection mode, convection. This is your conduction. Again, there is a convection. So, this convection responsible, who is responsible to convect this heat? Please tell me. Who is responsible to convection this heat, and who is responsible to convection this heat? Who is responsible? Please tell me. Who is responsible to convect this heat? Who is responsible to convect this heat? That is your natural convection. So there must be a natural convection, or there must be air flowing through this one. Okay. So let's suppose there is a flow of air. So this is your 20 degrees centigrade. This is your 20 degrees centigrade, let's suppose, and there is 27 degrees centigrade, and this is, let's suppose, 20 degrees centigrade. So this is your temperature profile. 20 to 27. And 20 to 5 conduction takes place. So this is 5. Now this 5 to 20, again it will decrease. So this is a temperature profile. This is a temperature profile. Okay. Now my dear, from this point, let's suppose this point to this point, there is a difference of temperature. Let's suppose up to this level. Up to this level, why? Because up to this level, there is a much more temperature variation. Up to this level, there is a much more temperature variation. Why? Because above that, let's suppose there is a same temperature, but less temperature. Why? Because it is very nearer to the wall. This line is very near to the wall. So very near to the wall, very appreciable drop in temperature. Very nearer to the wall, very appreciable drop in temperature. So that is called immediate surrounding. What is called? Immediate surrounding. So this is your immediate surrounding. Okay. This is your immediate surrounding. This is concept of immediate surrounding. This is called immediate surrounding. Okay, now. Okay. What amount of heat transfer here? Heat will transfer at 1035 watt. Clear? this is heat will transfer. No. We have to find it. What you have to find it? Number A, entropy generation is rate of entropy generation through wall is what? And number second, you have to find rate of entropy generation total. Here rate of entropy generation. Yeah. Rate of entropy generation of wall. Here rate of total entropy generation. Clear? This is total entropy generation. And the process, what is that? Process is steady. Process is steady. So if the process is steady, rate of entropy for a that means ds by dt of a control volume is 0. Steady state. Now, so what is the entropy balance now? Entropy balance. What is the entropy balance? What is the entropy balance? What is entropy in? That means rate of entropy in minus rate of entropy exit plus rate of entropy generation plus rate of entropy change with respect to time of a control volume. This is your entropy balance. This is your entropy balance. Now, this is 0. Why? Because steady. Why? Because steady. Now, so this is the, and this is what, beta? This is what? Rate of entropy transfer. Q in is equal to Q out. Yes. Q in is equal to Q out. Yes. This is your rate of entropy transfer. Rate of entropy transfer. My dear, please tell me, everyone, who is responsible to transfer the entropy? Under what mechanism entropy will transfer? Please tell me. Rate of entropy transfer by which mechanism? How many mechanisms you transfer the entropy? Please tell me. How many mechanisms you transfer the entropy? How many mechanisms you transfer the entropy, please everyone? Only heat and mass. These two mechanisms will transfer the entropy. But under how many mechanisms the energy will transfer? Energy will transfer by 3 mechanisms. Heat, mass and work. That is the main difference between entropy balance and energy balance. Energy balance, the transfer of energy is responsible by 3 forms: heat, work and mass. But what is the entropy balance? Entropy is transferred by 2 mechanisms only, heat and mass. But in this case, there is no mass transfer. Only heat transfer will take place. Okay. Now, who is the responsible to heat generation, entropy generation? Please tell me. Who is the? Yes, mass flow. Correct. Correct, Rahul. Correct. Who is the responsible to generation entropy? Please tell me. Who is the responsible to generate entropy? Please tell me, who is the responsible to generate the entropy? Who is the responsible fellow to generate entropy? Irreversibility within the system. Irreversibility within the system. If the irreversibility is 0, the entropy generation is 0. In that sense, the rate of entropy transfer is equal to rate of change of entropy. Okay, so this is the, and this is the, who is the responsible due to the unsteady state, but this is the system and surrounding irreversibility. That means irreversibility. This is for the irreversibility. That means, see my dear, any what I'm telling you, it is not, you know, I know that, you know very well, I know that. But I am telling also about how, what is the process. If someone asks you, who is the responsible to transfer the entropy? Sir, heat and mass. Who is the responsible to transfer energy? Heat, mass and work. Who is the responsible to generate the entropy? Irreversibility within the system. These are the exact answer. Other thing, you know, I know that. But these are the exact answer. Okay, how to reply. Okay. Now, so here in this case, that means this is 0. That means what is the next? That means S dot in minus S dot exit plus S of generation. Yes or not? Is equal to 0. Now, here this is only by heat. Here only heat. Yes or not? In this situation, beta, in this situation only heat, no mass. Okay, so only heat. So let's suppose this phase heat in, this phase heat exit. So this phase heat in, let's suppose this is a control surface, this phase heat exit, this is a control surface. So heat is in, and in this phase heat is out. Heat in is positive, heat out is negative. So entropy in, that means Q dot by T at in minus Q dot by T at exit plus S dot generation. Okay. Now, what is heat transfer? They are saying that 1035. What is the inlet temperature Ti at this point? This heat transfer at this surface. This surface temperature is what? 20 degree. This surface at which the heat will exit, this temperature is 5 degree. Put in Kelvin. 20 plus 273 minus 1035 plus 5 plus 273 plus S generation of the wall. This is in the wall is equal to 0. So S generation in the wall is equal to 0.191 watt per. Clear? This is clear, beta? This line is clear? This is clear, na? This is clear, everyone please tell me. This is clear? This is clear or not? Please tell me, beta. Now, we have to find the total entropy generation. How to find the total entropy generation? How to find the total entropy generation? How to find the total entropy generation? My dear, very important thing I am telling you. Very important thing. Many students get confused here. Many students. If we take this temperature is the system boundary temperature here. If we take this temperature of the surrounding, that is the total. See, my dear, I give you a very subtle concept. This is the ending session. I will give you a very subtle concept. 99% students get confused. What is that? See this one. See this one. Very subtle concept. Very subtle. Lastly, very subtle concept. See this one. See. See this one. Okay. So this temperature, let's suppose T1. This temperature is T2. This temperature is Ti. This temperature is Te. Yes, system plus surrounding. Now, same equation is valid. Let's suppose this is the inner temperature. Inner, and this is your T outer. Now, if we write, and heat will transfer. Please be careful, heat will transfer. If we write Q by Ti, T1, Q dot by T1 in minus Q dot by T2 plus S generation is equal to 0. If we write Q dot by T inner minus Q by T outer plus S generation dot is equal to 0. What is the difference between these two generations? This generation is within the wall and this is for total. That means system plus surrounding. So if we write the temperature of the surrounding and then you calculate the generation, that generation is total. If you write the temperature at the system boundary, that generation is for the system. So the generation you have to be very clear, this depends upon the temperature or what temperature you have to take in. If you take in the temperature of the system boundary, if you take the temperature of a system boundary, that is the temperature of the system. If you take the temperature of outer surrounding, if you take the temperature of outer, that means extended system, that means system plus surrounding. This is included system plus surrounding. That means you are taking extended system. So this is your system and this is your surrounding. So here the generation you have put the total. Now, if this wall temperature entropy generation, it is your S generation of the wall, it is your 0.191 watt per Kelvin, and if you calculate S generation total, this is your 0.341 watt Kelvin. Okay, my dear, tell me lastly, last question, today's last question. Entropy generation of the wall 0.191 watt per Kelvin. Entropy generation total is 0.314 wall per Kelvin. I'm not asking according to numerical value. I'm asking that why these two generation is differ, number first, and if we subtract these two different value, if we subtract two different value, that means if you subtract the entropy generation of total minus entropy generation of wall, so there must be a one generation. That generation, that means if you subtract, that means if you subtract S generation of total minus S generation of wall, how much it is? How much it is, beta? This is your 0.15 watt Kelvin. So this is also a kind of generation. My question is that this is the entropy of inverse. This is the entropy of the inverse. My question is that in this case, yes, Gautam, you are right. This is the entropy generation of the inverse. This is the entropy generation of the system. If you differentiate that, this is also kind of entropy generation. So who is the responsible of this entropy generation? This is my question. Who is responsible? This is entropy generation responsible due to within the system. This is entropy generation due to the system plus surrounding. But this entropy, if you differentiate this, who is the responsible to generate this entropy? Matlab, whose fellow to generate this 0.15 entropy generation? Okay, beta. Thank you. Bye-bye. Take care. One thing in the announcement is that if you see this beta, one thing in one announcement is that beta, one announcement is that see my again YouTube session will, this is my YouTube session, some question will discuss also about the that one, what is that called, basic, but this is the timing, this is the 4th of December at 6 p.m. to 9 p.m. Link will already descriptive in the description box, and the topic is advanced thermodynamics, and we will discuss much more intelligent problem also, and will improve better than today. In the next time, I will be present of you better than today. This is my promise. Okay? Okay, no problem, no problem. Okay. Okay, beta. Thank you. Bye-bye. Take care. We'll meet at 4th December from 6 p.m. to 9 p.m. with some very good question. Hi, beta. Hi. Okay, beta. Thank you. Bye-bye. Love you. Bye.